AI model based on input data layer and output data layer. Deep neural network make the pattern using Python programs library. Creating an AI model based on input and output data layers using a deep neural network in Python typically involves using a deep learning framework such as TensorFlow or PyTorch. In this example, I'll show you how to create a simple feed-forward neural network using TensorFlow to demonstrate the concept. Make sure you have TensorFlow installed. You can install it using pip bash pip install TensorFlow. Here's a Python program that demonstrates how to create a deep neural network for a pattern recognition task. We'll use a simple feed-forward neural network for this example. Python. Import TensorFlow as TF. Import NumPy as NP. Hashtag define the input data and output data. Input underscore data equals np.array, 0, 0, 0, 1, 1, 0, 1, 1. Type equals np.float32. Output underscore data equals np.array, 0, 1, 1, 0. Type equals np.float32. Hashtag define a simple feed-forward neural network model. Model equals tf.keras.sequential. tf.keras.layers.input, shape equals 2, hashtag input layer with 2 features. tf.keras.layers.dense, 4, activation equals ReLU, hashtag hidden layer with 4 neurons and ReLU activation. tf.keras.layers.dense, 1, activation equals sigmoid, hashtag output layer with 1 neuron and sigmoid activation. Hashtag compile the model. Model.compile, optimizer equals atom, loss equals binary underscore cross entropy, metrics equals accuracy. Hashtag train the model. Model.fit, input underscore data, output underscore data, epochs equals 1000, verbose equals 0. Hashtag evaluate the model. Loss, accuracy equals model.evaluate, input underscore data, output underscore data. Print, f loss, loss, accuracy, accuracy. Hashtag make predictions. Predictions equals model.predict, input underscore data. Print, predictions. For I in range, len, input underscore data. Print, f input, input underscore data I, predicted output, predictions I0. In this program, 1. We define the input data, input underscore data. The above program is a Python script that demonstrates how to create and train a deep neural network for a simple pattern recognition task using the TensorFlow library. I'll explain each part of the program in detail. 1. Importing libraries. Python. Import TensorFlow as TF. Import NumPy as NP. The program starts by importing the necessary libraries. TensorFlow is used for creating and training the neural network, and NumPy is used for data manipulation. 2. Defining input and output data. Python. Input underscore data equals np.array, 0, 0, 0, 1, 1, 0, 1, 1, type equals np.float32. Output underscore data equals np.array, 0, 1, 1, 0, type equals np.float32. Here, you define the input data and the corresponding output data. In this example, the input data consists of 4 sets of binary values, 0 or 1, and the output data represents the XOR function. You can change these data arrays to suit your specific pattern recognition problem. 3. Creating the neural network model. Python. Model equals tf.keras.sequential. tf.keras.layers.input, shape equals 2, hashtag input layer with 2 features. tf.keras.layers.dense, 4, activation equals ReLU, hashtag hidden layer with 4 neurons and ReLU activation. tf.keras.layers.dense, 1, activation equals sigmoid, hashtag output layer with 1 neuron and sigmoid activation. This code creates a feed-forward neural network model using the Keras API, which is a high-level API included in TensorFlow. The model consists of the following layers. Input layer, this layer has 2 input features, corresponding to the 2 binary values in the input data. Hidden layer, The hidden layer consists of 4 neurons and uses the ReLU, rectified linear unit, activation function. Output layer. The output layer consists of 1 neuron with a sigmoid activation function. This configuration is suitable for binary classification tasks. For compiling the model. Python. Model.compile, optimizer equals atom, loss equals binary underscore cross entropy, metrics equals accuracy. The model is compiled with the following settings. Optimizer. The atom optimizer is used to adjust the model's weights during training. Loss function. Binary cross entropy is the chosen loss function for binary classification tasks. Metrics. The training process will monitor accuracy as a performance metric. 5. Training the model. Python. Model.fit, input underscore data, output underscore data, epochs equals 1000, verbose equals 0. This code trains the model using the input and output data. The training process involves iterating over the dataset for a specified number of epochs, in this case, 1000 epochs. The verbose parameter is set to 0 to suppress training progress updates. 6. Evaluating the model. Python. Loss, accuracy equals model.evaluate, input underscore data, output underscore data. Print, f loss, loss, accuracy, accuracy. After training, the program evaluates the model's performance using the same input and output data. It calculates and prints the loss and accuracy of the model on this data. 7. Making predictions. Python. Predictions equals model.predict, input underscore data. Print, predictions. For I in range, len, input underscore data. Print, f input, input underscore data I, predicted output, predictions I0. The script makes predictions using the trained model and prints the predicted outputs for each set of input data. This demonstrates how well the model has learned the pattern. You can adapt this program for your specific pattern recognition task by modifying the input and output data, adjusting the model architecture, and configuring the training parameters accordingly. And the corresponding output data, output underscore data. This example simulates the XOR pattern, but you can replace it with your own data and desired pattern. 2. We create a simple feed-forward neural network model using TensorFlow's Keras API. The model has an input layer, one hidden layer with ReLU activation, and an output layer with sigmoid activation. 3. The model is compiled with the atom optimizer and binary cross-entropy loss, suitable for binary classification tasks. 4. The model is trained using the input and output data for a specified number of epochs. 5. After training, we evaluate the model's performance using the same input data. 6. Finally, we make predictions using the trained model. You can modify this code to fit your specific dataset and pattern recognition task by adjusting the input and output data, model architecture, and training parameters. Creating a detailed representation of a deep neural network, DNN, using ASCII art can be quite complex due to the many layers and connections in a typical DNN. However, I can provide a simplified ASCII art representation of the DNN mentioned in the program I provided earlier. This DNN consists of an input layer, one hidden layer, and an output layer. Here's a simplified ASCII art representation. Input layer, 2 nodes, hidden layer, 4 nodes, output layer, 1 node. Backslash. Backslash underscore 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 underscore. The input layer has 2 nodes, input features represented by a. The hidden layer has 4 nodes, neurons in the hidden layer represented by a. The output layer has 1 node, output neuron represented by a. Please note that this is a simplified representation and doesn't capture the full complexity of deep neural networks, which can have many more layers and connections. In a real-world scenario, DNNs can be much deeper and more intricate. Thank you.